kind of easy, right? It's like, and they're like waving, people don't know this. I'm like, I'm not trying to get you, but
Okay, so today we're going to continue the discussion of the Diels Alder Cyclo Edition and the importance of resonance structures, primarily starting off here in the dying, and how or where the location of the formal charges is going to help us predict how it will react with the unsaturated dienophile. And most of today's lecture will then transition into further conjugation, how that relates to color. So color as we perceive it on the visible part of the spectrum, and how extended conjugation, how molecules in foods give them color, and subunits that make up those molecules. So it's a little bit of, I'll claim, polymer chemistry, where we identify a monomer that polymerizes into a longer carbon chain, and then that will then have the property of giving a molecule color. So we left off on this discussion of resonance, and to recap, here is our butadiene system highlighted in red there. And what we've done is substituted a hydrogen atom for this electron donating group, so the methoxy group. And we want to determine how that methoxy group influences the resonance structures of the diene. So I want to number these 1, 2, 3, and 4. So the lone pairs of electrons using the curved arrow formalism push into that carbon 1 position, which means we have to break the pi bond between 1 and 2. So those electrons will go on carbon 2. So now oxygen is in a different bonding pattern than its normal two bonds, two lone pairs of electrons. So it's going to have a formal plus charge. Carbon 2 is going to have that lone pair that was on oxygen. So it has to be balanced out by a negative charge. So notice we're starting neutral, and in the resonance form we're showing charges, but they have to balance. So you don't want a situation where you have an excess of plus or an excess of minus. And then we can draw another third resonance form where that pushes down onto carbon 4. So basically what we're learning from this is positions 2 and 4 are electron rich. In the next case, we have the same 4-carbon diene, but now we've moved that substituent over to carbon 2. What you'll notice now is because it's now on carbon 2, it can only push those electrons to carbon 1. That pi bond between 3 and 4 is no longer involved in this resonance system. So carbon 1 is electron rich. So the last question on this slide says, what other functional groups can you think of that are characterized as electron donating groups? So our periodic table C, N, O, F. So what you saw just now, that's the ether functional group. So alcohols would be, so alcohols, ethers, so those involve oxygen. What about nitrogen? Those would be things like amines. Amides. So halogens, FCl, Bri. We'll talk more about their properties when we get to aromaticity. Those all have 3 lone pairs of electrons. To a certain extent, they can resonate those electrons, but then the issue is FCl, Bri. As you go down the group, so size increases. Basically, what that means is, if you think of fluorine like a golf ball, and like iodine is like a big beach ball, and carbon's just like a regular softball size. The softball and the golf ball are more properly matched. But when you get a softball and a beach ball, that iodine is so huge, those electrons really can't go back into the carbon, as sort of shown in this arrow here, if you had an iodine. So as the size increases, the orbital overlap is poorer, so they don't really participate in resonance. The line I would probably draw is sort of like right here between F and Cl and Br and I, when the size just gets too big. So those are electron donating groups. Again, pay attention, 2 and 4 positions, and then the 1 position when you're moving that substituent around. We're going to keep the dying part the same. But now we're going to use an electron withdrawing group at the 1 position, and then in the second case, it's at the 2 position. Let me just first expand out, before I draw a resonance form, the nitro group. The nitro group itself already has formal charges on it. So notice the nitrogen has 5 bonds, so that's not its neutral bonding pattern. So that's already going to be plus. And then that oxygen to the left has 3 lone pairs, 1 sigma bond, so that's going to be minus to balance the charge out. So again, for electron withdrawing groups, that if the atom bonded to the double bond already has a plus charge, that means it's taking that pi bond electron density out. So the arrow moves towards that substituent. So pi bond, and then we're going to break this NO pi bond. So now both oxygens are negative. The nitrogen still has the 5 bonds, it's positive. And so the other positive charge is now at carbon number 2. So remember, for the electron donating, that carbon position 2 was negatively charged. So we can draw one more. That pi bond migrates. So what this is telling us, C2 and C4 are electron deficient. So the next case, the substituent is now on carbon 2. It's going to pull electron density out of carbon 1. So notice the carbon pi bond between 3 and 4 does not get involved in this. So other electron withdrawing groups, just I'll do the 2 substituted. Those can be aldehydes, ketones, basically anything with a carbonyl group, carboxylic acid, the ester. We can, amides have carbonyls, so they can be electron withdrawing. And then finally, one more are nitriles, so that's C triple bond N. So those would all be electron withdrawing groups, because ultimately you can place a plus charge on the atom bonded to the double bond. So it's only this carbon here, position 1, that ends up being electron deficient. Yeah.
For the sake of example, is it just
so the diene and the dienophile undergo a 4+2 cycloaddition. So these numbers, you'll typically see them in like square brackets. You can think of them as atoms or p orbitals, because the p orbitals are on the atoms. You have to have 4 p orbitals plus the 2 p orbitals to do the addition. So it happens in a synchronous fashion. So synchronous means same time. So you have bonds forming and breaking at the same time. Concerted means that in this reaction, there's really no rotations or anything taking place. So along with synchronous and concerted, they sort of go hand in hand. And it says, given the product, what dienophile is used to create the Diels Alder product shown? So let me highlight in red here those 4 carbons. And the numbering I'm showing is just relative numbering. It's not the numbering that would be used in the naming of the compound. See the pi bond between carbons 2 and 3? So if we were to use this arrow, which means retrosynthesis, and we'll do more of this type of thinking as the module and the semester progresses. Retrosynthesis is like if you take your car or your little Lime scooter or whatever, that's a thing, right? If you start disassembling that thing into all its pieces, you eventually get to the starting materials. So it's a way of thinking about it. If I laid out all those pieces and asked you to put that car back together, that would be pretty hard, right? So it's just another way of analyzing molecules based on the reactions you've learned. So those 4 carbons are going to make up the diene, which means in the backward sense, carbons 1 to 2, 3 to 4 must have pi bonds. And that gets us back to our 1,3-butadiene. So highlighted in blue, those 2 carbon atoms have to come from the dienophile. And so if I put 1 and 2 there, the pi bond of that has to be between them. So phile just means lover in Latin or whatever. So you've heard of like hydrophilic. So hydro means water, so water loving. How many people are going into biochemistry? Okay, expected more hands to go up. So the terms in biochemistry, hydrophilic, hydrophobic, so phobic means hating. So hydro is related to water, and then the other terms are lipo. So lipo means fat, that's the carbon. So lipophilic, lipophobic, and that's important because, cell membranes, right? The membrane of a cell is what separates it from the aqueous environment of the body. So the answer for this is A. Those electron withdrawing groups, the CN groups, have to be on the same side. So it has to be cis. But how do we explain the 2 wedges? So those wedges mean, again, that's coming out towards you. So ultimately, they're on the same side of the 6-membered ring. And I'll try not to butcher this. When I draw it sort of large to give it perspective. Sort of down here, now I'm going to put the H's in. If you can imagine the dienophile in a plane, and I'll just sort of draw is that a rhombus, trapezoid? If that's a flat plane, the diene is going to approach from either the top or the bottom. I'm just showing it approach from the top. It's coming down. And you're going to make these bonds drawn with the dotted blue lines. So I'm not a very good artist, but those are the bonds that you're making. So sort of in bolded blue in the actual structure, you're making that. And again, in pushing the arrows, you're going to break a pi bond, make a new pi bond. This pi bond is going to come over and form a bond where that sort of blue dotted line is. And then that pi bond of the dienophile comes up and forms that sigma bond. So you can see from that geometry of the cis, those two cyano groups have to end up on the same side of the molecule. If we were to use B as the dienophile, the product would be this. And they would have a trans relationship. And the way you can understand that, so if you can imagine this sort of drawing, but instead of the cyano group here, it's on the opposite side. Over here, sort of under where the reaction's taking place. So that's what you have to watch out for, is basically you're identifying that pi bond. The pi bond indicates what diene you start with. The other two carbons inform you of the dienophile, but also the stereochemistry matters. So another example, here's your that's your diene. The other component is your dienophile. But now notice with the diene, it's connected back together to lock it into that S-cis conformation. So that's important for the Diels-Alder. And highlighted in blue, you can't lose track of those two carbons. They're still there. Nothing is happening at them, but they're still there. So I'll walk you through some of the wrong answers, and then we'll get to the right answer. So A cannot be correct because it doesn't have those two extra carbons that I highlighted in blue. Another reason is the dienophile has the E or trans geometry. So when you see those in the product, they have to be on opposite sides, a wedge and a dash. So C has the dash and the wedge, so it has that part right. But it doesn't have the bridge. So we'll say no bridge. No bridge. Say stereochem wrong. Here I'll say stereochem right. And so between the B and D now that we've eliminated the distractors, which one of those do you think is correct?
B.
So it's going to be B. So it might be hard to spot, so maybe I'll use green, but there's the, whoop, I won't do that. there's the ester, and then this ester, they're in the trans relationship. Here's the bridge, that 2-carbon bridge. So the reason D is not correct is that the esters now are on the same face as one another, which would require that your dienophile be cis. I neglected to put in a question slide after this. We talked a lot about resonance, so I want to circle back to why that's important, so we're not just dropping it off. So I'll try to write within the constraints of the space here. My iPad writing abilities are terrible. I just, the palette on this thing is driving me nuts. So if that was your diene, and your dienophile was say that aldehyde, you now have a choice. So I have the dienophile oriented that way, or I could orient it that way. And what the issue is, see that, this substituent, the O-methyl, is it going to be next door to the substituent on the dienophile? Meaning that, are you going to form that bond, or are you going to form this bond to here, where instead of being in a like a 1-2 relationship, it's now in a 1-4 relationship. And so you use those resonance forms to guide you on what the right answer is going to be. So I know it's going to get a little crowded, but this resonance form we said it can form that as a resonance form. Now the resonance form for the dienophile, the aldehyde is electron withdrawing. So we can push arrows like that. So that carbon gets a plus, there's a double bond, and then there's O minus. So the issue at hand is when those terminal carbons of the diene approach the dienophile, how is that dienophile oriented? So you can see that we want to match polarity. Negative is attracted to positive. So we're going to form that bond, and then we're going to form the bond from the other carbon back to this carbon bearing the substituent. So I can show this sort of stepwise, even though it doesn't happen this way. I'm just using the resonance structures to help guide us. Negative is attracted to positive. This negative comes down to reform the carbonyl. This pi bond hops over. And then we form those carbon-carbon sigma bonds. So this is going to be OCH3. And then we can see that the aldehyde substituent is right next door. So in terms of relative numbers, it's 1, 2. Because we've used the resonance to help us match the polarities. And a term that we used last semester, if you remember, when you're adding stuff to an alkene, this is called regiochemistry. You're deciding which carbon atom of the alkene gets what. So your quiz today will have, I mean, it's essentially this problem. All you're doing really, you're changing the stuff bonded. You're decorating the molecule differently. Again, what you're looking for is just the basic things you need. The diene must have, those 4 carbon atoms with the 2 pi bonds. You're identifying the dienophile, assigning it E or Z, and then how does it come together using the resonance to help guide you. So we learned about electrophilic addition to conjugated systems using, these diatomic molecules like H2 or Br2, or when you have these mixed systems with solvents. The Diels-Alder is a 1,4 addition, so make sure you know what those terms mean. Now what we're going to do is we're going to start taking that diene, look at trienes, tetraenes, pentaenes, and see how the effect of all those double bonds, like in a line, what is a physical property of that. So to review, let's talk about the electromagnetic spectrum. Some people just say EM spectrum. Spectrum, again, it's different from the word continuum. A continuum is something that goes on for infinity. Spectrum has sort of a start and an end. And don't pay too much attention to infrared spectroscopy. I think I copied a slide and didn't change it. But the first thing here is that's a wave. And you can see the wavelength changes from something short to something very long. A wavelength is defined from either the crest to the crest or the trough to the trough. So like that would be the crest. And that would be the trough. How do I spell trough? Trough, I think. So when you think about waves in the ocean, like if you could see one molecule of water, is that one molecule like continually moving forward towards the beach? Not really. The wave is just propagating. So the water molecule is kind of just moving up and down. The wave is the energy moving through the water. I mean, eventually it will move forward, but it's not riding that crest the whole way, you know what I mean? So I know it's abstract, and I'm 48 years old, and these things they're still hard for me to conceptualize. But again, we're thinking of how energy is propagated. So increasing wavelength just means it's longer. Decreasing wavelength means it's shorter. And there's an inverse relationship between the energy. So at a longer wavelength is lower energy. The shorter wavelength is higher energy. And down below here in this sort of next row, you see terms you're used to, like radio waves. So those are really long waves. Like, does anyone listen to AM or FM radio anymore? So that's coming over, a radio tower. Microwaves, you cook your Hot Pocket in your dorm room. IR waves, we saw that for identifying functional groups. And then what we're going to talk about today is visible. That's the only stuff that we as humans see. But again, we're surrounded by all of these waves like right now, and they're passing through your body, which is a weird concept. Once you get past that, you have ultraviolet. And so you're gradually increasing in energy. So X-rays, these are like your medical imaging, and then cosmic and gamma rays. So these are things that like neutron stars spin off, really high energy stuff. Does anyone here fly a lot? So when you go up in an airplane, you're getting doses of like radiation from the sun. So on Earth, the atmosphere protects us from that stuff. It sort of either bounces off or decreases the energy. But if you fly a lot, I mean, you'll eventually get past your OSHA sort of limit of radiation you're allowed to accept into your body. And that's bad because at higher energy, what's happening is you're interacting with like core electrons in your DNA. And so that sort of mutates your DNA in a bad way. So you've heard of these astronauts that are stuck in space because Boeing sucks. So they're getting a lot of, the thing's protected, but they're still getting that radiation. So with the visible spectrum, everyone's heard of Roy G. Biv. So I guess it's backwards here, right? Red, orange, green, blue, indigo, violet. So at higher energy is the violet, in lower energy is the red. So in IR, I means infra, that means before, so before red. So what is the chemical basis for color? First, what is color? So there they are. So within that part of the spectrum, you can see in nanometers on the right here where these different colors occur at what wavelengths. So again, red is lower energy, violet is higher energy because the wavelength is shorter. So we perceive color from 380 to 740 nanometers. Here's maybe a new term for you. To perceive something as colored, there must be a chromophore. So something that has to absorb light and reflect it back. That's how we perceive it. A chromophore is just a functional group that absorbs light. And so typically what we've been talking about so far are polyenes, carbon backbones with conjugated systems. What is the take-home message? The more unsaturation a molecule has, the more intense the color. And so now here's the color wheel. So as part of your gen ed curriculum, you have to take electives, right? Has anyone taken art? A couple people. Do they talk about the color wheel?
I mean, I took art appreciation, so not very much.
So they don't talk about this at all?
It was high school.
Okay.
Like 4 years ago.
So I took two art classes in college, which I really liked. I'm not very good at art, but I mean, I liked it. I like looking at people creating things. So why is this relevant to you? Think back to high school. You didn't want to be called out because you dressed bad. So when people dress, you want to use complementary colors, right? You don't want to clash. So complementary colors are basically opposite on this wheel. So if you pick like green, so green and red are complementary. And so if you look at a lot of college sports teams, they have like two primary colors and they're complementary colors. And I don't know, something about human perception, if the colors clash, you say it's ugly, right? I mean, you automatically make that judgment. So there's a Wikipedia link to a list of colors, and we communicate color based on standardized scales. So you're probably not old enough to remember, like, not maybe the first Nintendo, but maybe Nintendo 64. It came with a cable. The video cable was like 3 colors, RGB, and you plugged them into your TV so you got like better signal. So these color scales are based on, these combinations that when you mix things, they make the other colors. If you have an HP printer, anyone have an HP printer? So you buy these ink cartridges, right? So black, cyan, magenta, yellow, and they never print the number of pages they say they're going to print. And so that's a way they get you. But that's another way of classifying color systems. There's hue, saturation, and brightness for each color. And so humans have figured out a way of taking like these three characteristics of these colors descriptors. And one way of doing it is like hex codes. Another common thing for people in like marketing and business is called Pantone. If you go to like Lowe's or Home Depot at the paint section, there's like a couple hundred like swatches that you can get paint made of. Every can of paint you pull off the shelf is white. You bring them the swatch, they put it under this thing, and what it's doing, it's just dribbling in a couple drops of each of these to get to whatever code is on that swatch. And so that's why it's important, because like there's like 50 different yellows, you know what I mean? And they're all slightly different, and your eye can tell that. These two things, if you use Microsoft Word or, Word or Excel or PowerPoint, this is like the Crayola box. You can make your fonts. That's how I made these fonts, different colors. Here's the RGB. You can put in a number or the hex code. So color is really important in our everyday life. I mean, I'm drinking this Gatorade, which I don't normally drink because there's a lot of sugar, but it's blue. And I have perfectly good water here, but like think about when you go to the store and you buy something, what attracts you to that thing first? It's like color, like that can is yellow. If the can was like just aluminum, silver, or white, it's not as, you don't want to buy it. So color influences your emotions quite a bit. So we said that complementary colors are 180 degrees on this wheel. So if something appears orange, that means that really what it's doing is it's absorbing the blue wavelength. So there's the appearance and then the absorption of the complementary color. And so this, interested people in the sense of, why is a carrot orange? Why is a tomato red? Why are grapes, grapes can be different colors, but why are they, like blueberries? Not many things are naturally blue. So they have a different type of molecule in them. And so in 1937, a couple Nobel Prizes were awarded, 1937 and 38. So in 37, it was shared between Howarth and Carrer for investigations on carotenoids, flavins, and vitamins A and B. So you've heard of vitamins, minerals. Those are things you need in your daily diet for biochemical processes to happen. In 38, Kuhn won the Nobel Prize for his work on carotenoids and vitamins. And so what you have to think back to, in like 1900, the structures of these things were not known. So these are people that worked in a lab to figure out what makes a carrot orange. So carotenoids are polyunsaturated hydrocarbons, and more specifically, tetra we know means 4, and then this new compound terpenoids, which we'll talk a little bit coming up. Carotenoids are typically yellow, orange, or red. There's two classes called carotenes, and that's C plus H only. And then xanthophylls, C plus H plus O. And so carotenoids absorb wavelengths from 380 to 565. That's the violet to the green light. So therefore they appear yellow, orange, and red. at the lower energy, 565 to 740. So remember, the color you see, the material's absorbing the complementary color. So this is the structure of lycopene. It's a photosynthetic pigment that's a polyene responsible for giving the red color to fruits such as watermelon, grapefruit, and papaya. You know, as a review, we're communicating that structure as lycopene, but there's the IUPAC name. You can see it's really long, so lycopene will suffice. So there's a question, do you notice a repeating pattern? And sort of if you start at the end and work your way into the middle, the repeating pattern is 5 carbon units. So that's the repeating pattern. And so when you get to the other side, it sort of flips. So there's these, that's the monomer, that 5 carbon unit. And basically these enzymes come along, they polymerize it to make these things. One enzyme is called the lycopene cyclase enzyme. So that lycopene interacts with an enzyme, and an enzyme is just a reagent in biological sense that will carry out a transformation. So cyclase means it's going to cyclize it. So here's beta carotene. And so this gives the orange color to vegetables like carrots, sweet potatoes, and cantaloupe. And you can see just by that enzyme cyclizing the terminal carbons to make these rings, now you have a different molecule, has a different color. Let me highlight the conjugated part. So again, there's a double bond. So that's the conjugated system. So blueberries, blackberries, eggplant, grapes, red cabbage. This is a different class of molecules. It's still conjugated, but it's not like linear like we saw before. So these are called anthocyanins. And they have this core structure here. I'll sort of fill in red. And I have this term over here, flavillum cation. That's what that is, that O+. And then you have all these other you have what I'm saying are these R groups. Those are typically like glucose molecules. Glucose is a carbohydrate, and we'll talk about those in Module 2 when we talk about alcohols. But it's a different type of structure. You can see that it's still conjugated. I'll show these in blue. You have these pi bonds. So that's still a conjugated system. So what's in here? It says at the end, blue number 1. So that's how this is blue. There is a chemical in here, a dye that's been approved by the Food and Drug Administration to go in there and make it blue. And so, you know, these like Fruit Loops. I like Fruit Loops. What is Fruit Loop made of? some grain or something, right? You know, if corn, something like, if you go into like a wheat field or a corn field, like, you know, wheat is like light amber or yellow, corn is yellow or white or whatever. I think there's blue corn. You could,
When you grind it up, it's not very blue, it turns a little bit gray.
yeah, so it changes color, but you know, anything that's processed has a food dye added to it. And so again, you know, when white light, so this is white light coming from the ceiling, that's all of the Roy G. Biv, right? If you had a prism, you could then separate it. So, you know, for a dye that appears blue, that's the transmitted light. It's absorbing the complementary colors. And so all of these artificial dyes are a chemical that's added into food. And so that's why people are concerned about, you know, it's just added in there so you buy it. You're not tasting blue unless you have, you know, was it synesthesia or whatever, where you you can like taste color or like hear taste or something, you know, like where your senses are disconnected. So it's primarily a marketing thing. And so here are the names of those. So blue number 1 is called Brilliant Blue FCF. The molecular formulas, they're pretty big. If you want to look up the structures, you can just go to Wikipedia and look at them. But typically, you know, they have extended conjugation. So one thing we all learn pretty early on in our education is, you know, why are plants green, that sort of thing. So chlorophyll is a natural photosynthetic pigment. Well, it's a natural photopigment, not synthetic. That's present in plants, and it converts light into chemical energy. And so that energy provides downstream for electron transport chain. And so at that point, we're out of my realm of expertise. You would go into, you know, your biology courses to learn what happens after that. But basically, you know, plants absorb sunlight, energy gets transferred, things get metabolized. And then, so one of the products of metabolism is oxygen, right, for plants. Like when you breathe out, you're primarily breathing out carbon dioxide, and that's from glucose being metabolized. So it's good to have plants around. They produce oxygen that we can breathe in. So in 1930, Fisher won a Nobel Prize for his researches into the constitution of Haemen, chlorophyll, and the synthesis of Haemen. So the conjugated system here, I'll highlight in blue, are these double bonds that move along that bigger ring. So plants use chlorophyll, we use heme. Heme is a conjugated system with iron in the middle. When you breathe in, the O2 goes to that iron, and then it gets transported through your red blood cells. So UV vis spectroscopy, it's electronic spectroscopy. I'll explain what that means, electronic. Describing the absorption of energy from electrons by orbitals in a molecule. That's why we looked at those p orbitals for an alkene, a diene, and we'll see higher order ones now. The change in energy, delta E, promotes an electron from the highest occupied molecular orbital into the higher energy antibonding orbital, called the lowest unoccupied molecular orbital. So the reason you're seeing colors is because electrons are being promoted from one place to the next. Then they relax and things are emitted as light. The HOMO-LUMO gap, delta E, is described by this equation. Delta E equals Planck's constant times the frequency of light. And then, you can do these substitution things from physics, where now you're accounting for the speed of light, and then lambda is the wavelength of the light, typically in like nanometers. So UV vis spectroscopy, there's what an instrument looks like. You may do this in Gen Chem. If you take analytical chemistry, you'll use this instrument. So A is absorbance, and it's equal to the log of the intensity of the reference beam divided by the intensity of the sample. So you make up some reference, then you have your actual sample, and you get a quotient of those two, and that tells you the absorbance. And so this is called Beer's law. So epsilon times B times C. Epsilon is called the molar absorptivity, and that's specific to each individual compound. C is the concentration of the solution you make up, and then B is the sample length. So like right here, what you see, that's where you put your sample, which is a cuvette. A cuvette, it's like if you imagine a square and you extend it into 3 dimensions, I don't know what you would call that, but that's the shape of the cuvette. It's only like that big. So the path length, I think, is 1 centimeter or 10 millimeters. So you don't need much to do these. And again, what it's telling you is how much light can be absorbed by the sample. You can measure it for any compound, but keep in mind the compound has to have a chromophore. It has to have extended conjugation. So the instrument will still give you a number, but if it's outside what you see, it's going to be higher or lower than the visible range. And so the color we perceive is due to the extent of the light being absorbed. So again, here are the wavelengths. So shorter wavelength, higher energy is violet indigo. Longer wavelengths is lower energy, and those are red. So now this is where I was getting back to, talking about those numbers. So ethene, that's just 2 carbons with a pi bond. So notice what I'm saying, lambda max. The instrument is producing a curve, whatever shape it looks like. The top of that curve is called the lambda max. That's where it absorbs the most light. So ethene is 171, and what you'll notice is it doesn't fall in the range at which we see. So if you had a clear container of ethene gas, it would be translucent, like colorless. Now when we go add on a double bond, we get to our Diels-Alder precursor, that butadiene. Notice the lambda max change as it now increases. So we have to get up into the 380 before we start seeing it. This other term down here, the pi to pi star, and then you have this value, 700 kilojoules per mole for ethene. That's the HOMO-LUMO gap. That's the energy required to promote an electron. And then as that electron relaxes from the LUMO back to the HOMO, that's when the light is emitted. And you can see as we can add a substituent, so we get to isoprene. We can add more conjugation, we get to the hexatriene. we can get to the tetraene, and you can see that the wavelength is gradually increasing, but the gap energy is decreasing. So as you add more double bonds, that energy becomes lower. So why is that important? When you look at a carrot, it's orange. You see it as orange. That means that HOMO-LUMO gap is really small because you're already in the visible region. So visually, what does that look like? So this first case is, there is your ethene. Each carbon atom is supplying one p orbital. So for example, if we sort of drew them in here, there's a p orbital, there's a p orbital. They overlap to form a pi bond. Because we have to conserve orbitals, this is pi star. So that the arrow in red here, that difference, that's that HOMO-LUMO gap. You can see that it's really big. But then as we start adding double bonds, so now this next molecule is the butadiene. There's 4 p orbitals, so we have to have 2 bonding, 2 anti-bonding. Now that gap is getting smaller. Which means less energy is required to then promote an electron up. So it gradually gets smaller and smaller and smaller as you add more alkenes, which moves the light into the visible region. So this slide is showing you what happens when you then promote that electron. So you've promoted up into pi star. It's when you promote it, it's higher in energy. It doesn't want to be that. So it's ultimately going to go back down. And what it's doing at that point is releasing energy in the form of light. So these photons that we're seeing. So we'll look at a qualitative set of rules called the Woodward-Fieser rules. So this is Woodward. This is Fieser. They worked at Harvard. They got together and figured out these rules on an empirical basis. So they had like a library of different compounds. They used this instrument to measure these values, and they started noticing trends. That's what empirical means. You see all this thing, what's normal, what's abnormal, how do we explain it? So basically, we're going to start off with a base number of 217. So 217 corresponds to the 1,3-butadiene. That's the benchmark system. And then as you start substituting off different groups, either adding alkenes or different groups, that number is going to increase. So the 217 is going to get greater. That moves it into the visible region. So you would add another alkene to that, and now you're up at 258. Now you have a tetraene, you're at 290. So it's a way of estimating the lambda max, the maximum wavelength at which it absorbs for any structure. The starting point is the butadiene at 217, so that's the core that you're looking for. For every double bond additionally that you add, that adds 30 nanometers to the 217. For every substituent that's not a double bond, so we have a methyl group, that's called an oxychrome. That gives you +5. So a couple other more specific situations. If your diene is in a ring, so there's that diene. And an alkene happens to be outside, that's what exocyclic means. That adds 5. Exo means out. If you have the diene within a ring, that's called homoannular, that adds 39. If they're in two different rings, that's called heteroannular. So that one's different. You don't start at 217, you start at 214. So we'll do a quick calculation here. We need to remember the numbers, so I'm going to slide back. Okay, so looking at this structure, there's the diene. So that starts at 217. Notice it's within a ring, so it's homoannular. So that adds 39. Now this is the tricky part, identifying the substituents, the oxychromes. So I'll highlight those in blue. There's 1, there's 2. So these other things here that I've highlighted in green, that's already folded into the homoannular calculation. So the oxychromes account for 10, which is oxychrome. You're 5 times 2. So we add that together, we get 6 plus 1, 3, 4, 5, 6. So that's going to give us 256 nanometers.
Yeah.
What? 266. I can't even do math. Again, this type of problem, in preparation for the exam, you're just looking to apply those rules, figure out which answer is closest, and then ultimately the value of that is, is it going to look clear, or does it fall in the visible region? Will it have a color? So we want to, in this problem, estimate the lambda max for lycopene. And so our core is that. That's the 217. And then the question's asking you, what is the estimate for the conjugated pi bonds? So we're not really considering the oxychromes at this point, just the continual alkenes. So each one of those adds 30. So we start at 217. So that's that. So I'll highlight in blue. There's 1, 2, 3, 4, 5, 6, 7, 8, and 9. See these over here? That alkene there and this alkene at the end. Those are not counted because you have sp3, sp3. You're breaking, those are isolated. They're not conjugated into that system. So what do we get? 30 times 9, is that 270? Our base is 217. So 487 nanometers. And so now we're in that visible region. So 487, now we have to account for the oxychromes. Those are the substituents that will increase the lambda max beyond 487. How many oxychromes do you count just based on the conjugated part of the molecule? So the initial 6 are pretty obvious, right? So oxychromes, 1, 2, 3, 4, 5, 6. But keep in mind the other part there, that's an oxychrome. 7 and then 8. Because it's still bonded to that carbon. You have to count it, just like you count that methyl group. So that gets us 5 times 8 is 40 nanometers. So 487 plus 40. Ultimately gets you to 527, but the answer for this would be B, plus 40. So I'll take just a 2-minute introduction on terpenes. This stuff will not be on today's quiz. Today's quiz is more deals Alder type stuff. But I'm going to give you your money's worth here. So we mentioned that lycopene was made of these monomers. And so lycopene is, in general, a functional group called a terpene. And derivatives of terpenes are called terpenoids. And in 1939, Butenandt and Rijiko were awarded the Nobel Prize for polymethylenes and higher order terpenes. So they messed around with a lot of plants. They extracted things. They figured out the structures. They did combustion analysis to figure out molecular formulas, that sort of thing. The polyenes that we saw are classified as terpenes. And terpenes are further classified as lipids. So lipids gets into your biochemistry, cell wall membranes, that sort of thing. They're constructed of this compound called isoprene, which is 2-methyl-1,3-butadiene. So again, there you see that system, that 4-carbon system. You have this methyl group at position 2. That's the monomer. So I have that written somewhere. That's the monomer that will polymerize in all of these cases. Today's Wednesday, so next Monday we'll look at more of these. Next Wednesday. So next Monday is a holiday. So isoprene will polymerize. So in one case, natural rubber forms this polymer that has the Z configuration. It can polymerize another way to form the E configuration, and that's called gutta percha. And so why is that important in the development of things? At some point, someone figured out, hey, I can take rubber and heat the crap out of it and then stick it on a car to make a tire. So if you're, I took the slides out of this, but if you're interested, read about the Democratic Republic of the Congo. That was a huge source of natural rubber. The Europeans went in there and colonized it, brutalized it, but it shows you the effect of these compounds, how they're ultimately transformed into stuff that we use. I mean, every vehicle has a tire, right? So we'll further talk about other smaller structures of terpenes, like scented things, oils, natural scents. Those come from terpenes. We'll talk about those structures next Wednesday.